Hi, Femi. Thanks so much for joining me today. I really appreciate it. You've worked across environmental chemistry and contaminant analysis. What originally drew you to studying persistent pollutants like PCBs?
Yeah, thank you. I'm a chemist, as you know, and one of the things that I'm interested in monitoring things that are relevant in the environment. And as someone that grew up in Nigeria, I've seen a lot of people that suffer from diseases and things that they cannot explain. And one thing that I always want to do is to see how I can use my knowledge of chemistry to solve challenging world problems. And that's one of the reasons why I decided to see what is in the water that people are drinking, what is in the soil that people are farming in, the food people are eating, what is it that is inside it. And as I grew in my knowledge of chemistry, I became an organic chemistry, and that now make me wanting to know more about organic pollutants in the environment.
What should the audience know about this region in southwestern Nigeria from either an industrial or an environmental standpoint?
So Nigeria is a growing economy, and southwestern Nigeria, where we have Lagos, Nigeria, is one of the brain behind the economy of Nigeria. There's a lot of industrial growth. The population in that area is dense, and there are a lot of activities that is going on there. There are ports where things that come from overseas enter Nigeria, and many things are going on there, and there are a lot of rivers around southwestern Nigeria. And one thing is that there are a lot of development in that area, but still there's a lot of activity that is going on with those rivers. For instance, some people are still drinking from the river, some people are still using those rivers for agricultural purposes, and a lot of activities, fishing and other things are still happening in those rivers. And that is why we decided to monitor those rivers to see, are they contaminated, are they okay. And funny thing is that we, like PCB, we have monitored different pollutants. Like PCB, as you know, is a legacy pollutant.
Yeah, and I'm glad you touched on that as far as for listeners who think that PCBs are mostly legacy pollutants, why are they still such a big problem today?
So one thing is that something have been regulated that you should not use it. Another thing is that something have been banned. So PCB, as we all know, is legacy. It has been banned. Nobody is really producing it again. But the fact is, some of the old transformer, for instance, some of the old electrical equipment, some of them still contain this pollutant. And now, when there's rainfall, when there's this rain wash some of the pollutant off to the river. And beyond that, when they use them in those olden days, some of them that got to the river, they settled in the sediment. And now when you disturb those river, they remobilize back to the surface water. And that is why monitoring them is very, very important. That something is legacy, that something is outlaw, does not mean they are no longer in the environment.
What makes PCBs particularly challenging analytically and environmentally compared to other contaminants, and why are they so persistent in aquatic systems?
So one thing is that PCB is hydrophobic. When we say something is hydrophobic, it means it does not, it's not something that is water loving. So because of that, it settles in the sediment. And as they don't easily degrade, they are not thermally degradable. And as a result of that, they get into the sediment. And when they get into the sediment, if you disturb the sediment at any point, they come back to the surface water. And again, they have different congeners. And those congeners, they can get buried in the matrices that you have in the water. Water, the river, is a complex system where you have different things. So when you want to separate them, you get them mixed up with different things, and it's always very difficult to separate. And again, because those things have been outlawed, you see them in trace amounts. And when you see them in trace amounts, sometimes people will not see them. They will just say, oh, nothing is there. So you need to pay careful attention and use the right instrument, the right method before you can detect them.
And feel free, if you could, to talk about this in general terms. Could you walk us through the full analytical workflow from the river water collection to the final quantification?
So what we do is to get a composite sample. We get sample from different rivers, and then we get them inside a glass amber bottle. We use glass amber bottle because we don't want to pollute the water. And we use amber just to ensure that we protect the integrity of the pollutant. Then we normally add sodium azide. The reason why we have sodium azide is to prevent microbial degradation of those things. And then we store them in a cool environment just to ensure that microbial activity are reduced. After that, what we do is to do what we call liquid-liquid chromatography. Generally, liquid-liquid chromatography or separation, generally, it means that we are separating between two phases. Now, this liquid, it happens to be solvent. We are using solvent to separate the solvent. And we use separating funnel. We put our liquid inside separating funnel. We add DCM to it. And the reason why we use both SN and DCM is because we have some polar and non-polar part of PCB. So we want to extract them completely. And after extraction, we normally do what we call concentration. We want to concentrate the PCB. That is one of the sensitive things that is very important when you are doing this kind of analysis. After we have done the concentration, we do cleanup to ensure that if there's some interferences, we remove those interferences. And after that, we reduce and prepare it for the GC-ECD that we use. After we quantify it, then we try to look at the earth implication of the concentration that we determine, because concentration alone does not make sense to people that are not chemists. So we try to convert it to something that will make more sense to our audience.
Were there any specific reasons why liquid extraction made sense for this application compared to something like a solid phase extraction?
Yeah. So generally, we could use solid phase, but one of the reasons why we decided to use liquid extraction is because we want to be sure that most of our congeners are not trapped inside the solid phase. That's one. Two, because we are dealing with a very large volume size again, and sometimes when you use a solid phase, if you're not very careful, sometimes those solid phase can get clogged, and you know, so that's why we decided to use liquid extraction.
You had mentioned the cleanup step. How do you handle cleanup to reduce matrix effects?
So we use silica aluminum. And one of the reasons why we use silica alumina is because it's very effective in removing other matrix interferences that are not PCB. So that's why we decide to use that particular one. And as you know, cleanup is very essential. Otherwise, you will mess up what you want to do.
One thing I thought was particularly interesting when I was reading the paper was the choice of GC based detection instead of LCMS, because I would have figured LCMS would be the way to go.
Yeah. So normally, because we are working with liquid, the first choice would have been LCMS because that's liquid chromatography. But GCMS has to do with when you are working with something that is volatile. Most of these PCB are volatile, and that is why we decided to use GC. So when you are dealing with volatile, you want to use GC. And again, when we are separating it, I think GC tends to separate more, than LC. So that's why we go with GC.
And if you could, why an electron capture detector for this application?
So generally, people like using MS because MS can give you identification of wide varieties of things. But now, when you look at selectivity and specificity, electron capture detectors are known to be very good for chlorinated compounds. And so when we consider the level of, I mean, the concentration of PCB that are in river, river is a diluted system. That is why we decided to use ECD because we know it's very sensitive. And again, if you look at the detection level that we expect for that kind of thing, so we need something that we can go to a very low detection level. So that is why we decided to use ECD because the detection level we are expecting
And you may have just answered this, but were there any other advantages that GC-ECD provided for halogenated compounds like PCBs?
Yeah, just like I said, sensitivity and selectivity are the main thing. And the level at which we can go down, so that is one of the reasons why you preferred ECD over MS.
And how did you validate recoveries and detection limits?
So what we did is first of all to spike a surrogate standard. So we use surrogate standard. Normally we like to use certified reference material, but when you don't have that, you decide to use surrogate. So we use the surrogate and we spike it, then we try to see the recovery we have. And the recovery we have, if I can remember, is close to 100, between 85 to 114% recovery, which is great. And also we calculate our limit of detection and we decide to use when our limit of detection is around 3 to noise ratio. So that's what we use.
Environmental water samples are often extremely dilute. How critical was concentration to reaching your detection limits?
So if there's anything you must not play with is concentration. If you don't concentrate it, you will not get anything. And so when we are concentrating it, we are very careful and you don't want to rush the concentration. If you rush the concentration, there's possibility, like I've said, these things are volatile. There's possibility that you lose most of this PCB and all what you'll be seeing is not detected. So you do it gently. For instance, when we are using rotary evaporator, we try to ensure that we don't use high temperature. We ensure that we don't dry completely.
And that was a big question I had because I did notice that you utilized both a rotary evaporator as well as nitrogen blowdown. So I was curious to hear how both of those techniques worked well together in concert.
So generally, when we are using large volume, you want to concentrate down, we use rotary evaporator. So after we want to recover our stuff from the rotary evaporator, we use another solvent to recover it. Then we now use nitrogen blowing to concentrate it down so that we now use that to prepare it for our GCMS.
And you noted that you didn't go all the way to dryness. Do you remember offhand how low you took the volume down?
Yeah, I think if I can remember, we always try to ensure that it's less than 1 mil. Yeah. Very small amounts. That's what we normally.
For labs setting up similar methods, what practical tips would you give for solvent reduction without analytic loss?
I will always tell them that they should be careful with their temperature. They should not use high temperature, and they should pay attention when they are doing concentration because that is where many people, miss it.
You looked at both seasonal and spatial differences. Why were wet season concentrations higher?
So, like you have noticed that high wet season is always higher than the dry season, and we were surprised initially because we were thinking that dry season should give us a more concentrated sample. But of course, during raining season, rain is falling. Most of the whole transformer that they have in those regions, the rain is washing them off, and every time, and where we have already sediment, there's a resuspension. That's one of the reasons. And again, temperature is cooler during that time. So your PCB will not potentially evaporate. So what we saw is that every time during rainy season is always higher than during dry season.
Can you explain how toxic equivalency helps communicate risk?
Yeah, like I've said at the beginning, is that just concentration alone does not make meaning to people outside the field. And what we do is to convert the concentration of different congeners of PCB we have to single value that is biologically relevant. And normally we compare it to dioxin because many people know the toxicity of dioxin. So with those single value, you will know that okay, if it is above this value, it means it has this effect. If it is below this value, it has this effect. So that is why calculating the toxic equivalence value is very important.
If you had funding to expand this study, what would you measure next, whether it be sediments or fish tissue?
Sediment and fish tissue, like you have said, they are very important. One is that sediment helps us to know what is inside there, possible that there's possibility for it to resuspend again. Why monitoring fish or fish tissue tells us what that people have the potential of taking in. People eat the fish, and once they eat the fish, as you know, PCB can bioaccumulate in the body system. So if you get one fish today, if there's a little percentage in it, it can bioaccumulate in your body. You get another one tomorrow. So that is one of the reasons why we want to monitor those things.
What would you recommend labs or regulators prioritize first? Monitoring, remediation, or prevention?
Of course, without monitoring, if you don't know if it is there, you will not be able to prevent it. So monitoring is very important. The long goal is to prevent, but the first thing is always to monitor. When you monitor, you know it's there, then you can plan on what to do next.
Where do you see analytical chemistry having the biggest impact on environmental protection over the next decade?
Analytical chemistry will keep to be at the interface of chemistry and application because with the knowledge of analytical chemistry, we'll be able to understand what is present in the environment. We'll be able to understand how best to monitor them. We'll be able to do a lot of things which will invariably help in the prevention of those pollutants in the future.
Is there anything you would like the audience to know about your work that we haven't covered today?
Yeah, generally, we are interested in working at the interface of chemistry and biology. We are interested in working at the interface of things that help to make life of people better. So we do a lot of things, not just monitoring. We go to the extent of developing material like catalyst to remove or degrade those pollutants when we see them in the environment. Monitoring is just one part of our work. Developing material is another part.
Well, I greatly appreciate your time today, Femi. Thanks so much for sharing your work with the audience.
Thank you for having me.